So back to the second session, we considered that after a wonderful piece of work, what is left to complement this? We just try to approach the same problem or a similar problem by using a 3D deep foundation analysis software, RSPile by Rocscience. It's worth mentioning, I have put my colleague Berk in the first place because he was the one who prepared the model actually and just gave me an overview of how I could handle the presentation. So not 99%, 100% of the credits goes to my teammate. He's a MSc candidate in geotechnical engineering and he's a part of our group. To give you a small, short outline, we will just deal with RSPile capabilities in case you have not encountered any use or any hands-on exercise with what RSPile can do. Then we will just switch to a very basic walkthrough of how a capacity of a single pile can be calculated. Then approach to model a very similar problem to the ammonia tank problem that Dr. Miller explained by just modeling the pile group with CAP and see what benefit can we get out of it to supplement any further analysis. So a very quick overview of RSPile and Plus version. The basic features enable it to analyze the behavior of vertically and laterally loaded piles. Of course, you can analyze pile groups, and you can use RSPile material as a support element in conjunction with slide 2. This is not a discussion topic for today, so I'm leaving this for perhaps further events in case you're interested. The interface of RSPile is very basic, and right now the current version can support addition of multiple borehole definitions with different groundwater elevations and different profile elevations, so that you can actually model the 3D space with success. It also allows you to model very simple geometry in almost no time. For a single pile analysis, its capabilities are include modeling the behavior of laterally loaded piles by using nonlinear PY curves defining soil reaction as a function of lateral pile displacement. Back to axially loaded piles, it also simulates the nonlinear stress deformation behavior using the nonlinear TZ curves for pile shaft resistance and QZ curves for end bearing resistance. So there are a lot of models available in the literature incorporated within RSPile. They all have their assumptions and limitations, and nevertheless, they are very well documented, and links to original references are provided so that you are able to control what you're assuming and modeling. A very quick list of what you can do and the available soil models within RSPile in terms of modeling the laterally loaded piles and axially loaded pile analysis. Today, we will just cover a very basic subset of them. The rest is up to you to explore. Different pile types can be defined in different geometries, and almost all of them are parameterized, so you have total control of what is available in local and global practice as well. You're able to model variable cross sections, tapered piles. You're able to model your piles in terms of elastic, plastic, reinforced concrete, or press-stressed concrete materials with all their yielding strengths and capacities calculated accordingly and interactively based on the cross-sectional properties you interactively input your system. Different varieties of loading types are present, static, cyclic, and you can factor them according to RFT. It's not only a design approach used locally in the US, but over the globe as well, in some parts of the world, at least in our geography. Lateral loading conditions, you can load the caps or individual piles using shears or displacement profiles, moments or slopes, which would be beneficial in case you have the actual pile load test results in the field and want to calibrate or simulate your pile test to get a calibrated PY curve or a TZ curve. Different traction load application options do exist. We will not go through those in detail. You have the option to modify your PY curves and TZ curves in using multipliers, and those multipliers are custom defined, and those are used for modifying the behavior of pile groups, battered piles, scale effects, installation effects, error adjustments, and a whole lot more. Within a matter of seconds, you can get the results and the behaviors and what you need for just finalizing your structural detailing, providing input for your soil structure finite element model or your superstructure model to be detailed elsewhere in case where the pile, the raft, and the superstructure needs to be modeled either statically or under dynamic loads. So the options for group pile analysis are somewhat similar. You have the option to define circular, rectangular, and user-defined polygonal shapes for the cap. You are able to apply loading in 3 dimensions to the caps, and you can define patterns in no time. The lengths, the spacings of piles can be different, and they can be parameterized and generated within a short amount of time. Group effects can be modeled, and you have a variety of options to model the connection between the piles and the cap. In a moment, we will see in a specific example how they are handled. So back to ammonia tank model in RSPile, we humbly made an attempt to see if we can just reasonably model a similar structure in no time, which will just generate us some benefit in the design procedure. A specific remark or a disclaimer here can be that we were not after just one-to-one match between the parameters or the behavior of what Dr. Miller presented a moment ago. Although the geometry and most of the soil parameters were identically selected as the same, we are aware that some differences exist between the assumptions and our selections made intentionally to somewhat modify the model from our side. So please make sure that we're not seeking one-to-one correspondence between our attempt and the previous wonderful piece of work, but it is not a limitation to do so. The pile types, just a revisit of our previous problem. 117 piles, 88 centimeters diameter, 29 meters of length, cast in situ piling. The diameter of the raft, the cap, was about 39 meters, and its thickness was selected as tentatively as 60 centimeters. Let's see what different, yes. In order to start our problem, we have begin with determining the capacity of a single pile. Back then, in the earlier versions, RSPile did not have these options, but they are now included, and we have just made several attempts, as also provided in the original verification documents, that they are working perfectly okay to estimate the old-style spreadsheet solutions for determining the ultimate carrying capacity of driven or bored piles. The purpose is to provide an insight on how pile behavior can be modeled and pile reactions can be quantitatively assessed for structural detailing. Our options for soil properties are several. However, we have, in the specific example, simplified them to two categories, in fact: cohesionless and cohesive soils in terms of determining the capacities. Although weak rock is listed here and may be used for the marl layer where the end bearing is to be met, we have just modified the parameters to avoid any one-to-one match and direct comparison. The theory behind determining and calculating the capacity of a single pile is mostly available in the literature, and what has been preferred in RSPile software is clearly documented in the online PDF file, which you can access right now. For the soil properties, mostly we have used some parameters from the ammonia tank problem. For cohesionless soils, to determine the capacity, we have used the KS delta method. However, there are a variety of options you can use, such as the SPT Ashton method, user factor method, or the beta method. The second friction parameters are just for a reminder, quick reminder, listed here, and quick parameterization of Ks over Ko or delta over phi, which are a function of the construction method of the pile, are provided to modify the parameters in case you need. So the end bear, this concludes the part for determining the skin friction parameters for cohesionless soils. For the end bearing parameters, these are taken just directly from Peck, Hansen, and Thornburns. Assumptions and work, although you also have the option to calculate the bearing capacity factor from SPTM blow counts. You have a dialog box here, and you are able to enter the SPTM blow counts, the uncorrected ones, only energy correction applied. And what RSPile does is to estimate the internal friction angle using the well-available correlations. If you have anything in handy you might want to prefer, you're free to enter so. For cohesive soils, the alpha method is used, where in this case where the beta method can be used as well. So here's a quick reminder on what we have used for the skin friction parameters and the end bearing parameters. For the end bearing capacity factor and C in cohesive soils, a general approach of 9 is used. We have underlined general and should be aware that this is a general approach and may not be always the optimum parameter to choose. We did not prefer in this model, but in case you may want to work with weak rock, we have unconfined compression strength and some threshold skin friction and end bearing limit values to be input as the input parameters. And based on the alternative methods you may choose for estimating the skin friction and tip resistance within a weak rock mass, you have the following options available in the literature to be directly implemented in RSPile to estimate the capacity. And the second option is to just hop on to borehole editor of RSPile, similar to what you have in the finite element software and settle3 in particular to enter and define the thicknesses of each layer to come up with a very idealized soil profile and estimate the ultimate pile capacity of a single pile having a length of 29 meters. Worth to mention, our other assumptions were that the tank was directly located on ground without any prior excavation to make our lives easier, and the groundwater table was located at 6.5 meters from ground surface. Here, what we have as the general results in the RSPile software is that we have the skin friction capacity and end bearing capacity and the ultimate bearing capacity calculated and tabulated for us. We intentively choose these parameters for the end bearing strength values just for the sake of showing you that shortening the pile length can be of value in terms of increasing the end bearing, so thus total capacity and cutting down on production costs. This was left as it is, and no further modification was sought for this demo only. I know that this is not logical, and a revised pile dimensioning can be applied here for our particular problem scenario, our makeup scenario. The options, once you have solved the ultimate capacity of a single pile problem, is to export your data and charts and play it on a spreadsheet platform or a reporting platform, which you prefer. So back to group pile analysis. Having known these, we tried to simulate what is going on in case we attempt to just model a pile raft with 117 piles. So we switch our project settings to group pile analysis, and back to soil properties, we need to enter some other data. Now we have to make use of the axial and the lateral soil property definition tabs to implement our reaction curves and soil behavior curves for the lateral and axial behavior of piles on different types of soil. To begin with the axial capacity in a typical clay, we set the soil type to drilled clay, although there are many others you can use. The ultimate shear resistance is based on the averaged values we have preferred over that layer in our soil parameters. So the ultimate end bearing resistance is set to 0 because we're not expecting any end bearing from the topmost layer. So it's sort of back calculating what you have given and just entering it here once more in terms of estimating the axial capacity in clay and cohesion in the soil as well. What it does in the model is it makes use of the Reason O'Neill models for estimating the behavior of drill shafts in clay in terms of skin friction and bearing. So you will know how much strength is mobilized based on displacements within the analysis of RSPile. Worth to mention, a simple finite element model is created within RSPile where the pile elements are themselves finite elements. So upon the application of loads, the load deformation behavior can be modeled accordingly, and the soil reactions can be modeled. Unlike the RS3 or RS2 model, a finite element model, you don't have the option to just directly model the cap and the raft and the soil in an integrated manner. So it's some sort of a decoupled analysis, which you can use the results of RSPile and plug it back to a finite element software to continue if you wish, or you may just finalize your detailed structural design only with RSPile as well for typical problems. For the lateral capacities, we have used soft clay soil for the top most layer. A soft clay soil model uses the work by Matlock, where the ultimate lateral load, ultimate normalized lateral load carrying capacity is defined as a function of lateral displacement, and we are able to, of course, enter a strain factor, which is defined as a strain corresponding to half of the maximum principal stress difference. In case you don't have any idea of what that may be, and you are missing any theoretical data or field data from actual field loading tests, the references just guide you to make a rough selection of what may be appropriate for selecting the strain factor. And it's clearly documented within RSPile. Likewise, if we're in sand, for just estimating the axial capacity in a cohesionless soil, you have the option to use drilled sand, for instance, where you enter the ultimate shear resistance calculated likewise as in the cohesive soil range. However, this time, to calculate the load settlement behavior and the reaction curves of these piles, Wiese and O'Neill's developed charts for sand come into action and help you. So the major remark is, be sure to go along with the documentation the software has presented while selecting your soil models. For the lateral behavior in a sand, Wiese et al. 1974 is what matches your option right here. And a clear definition of your input parameters are described. You have to enter stiffness in the linear range at the beginning initial stage of the loading, which are different for the submerged or sand located above the water table. So once you enter the water table into your RSPile model and enter the coefficients, depending on which location the layer is located within your model, above or below the water table, the software selects the appropriate coefficient and continues the calculations for simulating your behavior in sand. For stiffer clays, under the water table, Wiese et al. 1975 says that the model has a linear range in the first stage of the loading, then reaches the peak capacity, then it in the residual phase of the loading, it has a different behavior compared with the loading stage, of course, and where it eventually reaches the total failure and has a cutoff on load carrying capacity after a certain lateral displacement. So this constitutive model is supplied by its all consistent mathematical formulations and just a general recommendations on what you may use for the input parameters. The ultimate end bearing resistance for the layer corresponding to pile tip is not entered as 0. Let's do not forget this. Having said all those, we're done with the layering and the soil properties. Back to pile properties. In this specific example, we have preferred the pile elements to remain as elastic. You also have the option to define them as plastic, where you can just enter the capacity and the system will behave accordingly after it reaches its capacity, or you may use reinforced concrete or pre-stressed concrete detailing, all included within RSPile, to interactively calculate the capacity. And before the stage you reach those capacities, it will behave as elastic, and after the capacity has been fulfilled, those cross sections will behave as plastic. So you have the option also to model the post elastic behavior and get the pile reactions. The capacities will, of course, be calculated on based on cross-sectional properties and custom reinforcement details. For simplicity, we have kept this as elastic. Now to defining the cap parameters. Please recall that we have several options to define the cap parameters in terms of geometry and other model specific details, and we have 5 different tabs for which interactively walks you through the steps of defining without missing anything. Here our cap thickness was selected as 60 centimeters, and we have been compatible with the original recommendation of the cap diameter. Back to pattern. Here you have the option to just manually enter one-to-one the X and Y coordinates of the pile. Tip locations, here we have just taken those locations directly from Dr. Miller's RS3 model in no time, just which enabled us to model the same problem within a relatively short amount of time. We have defined the pile lengths, and we have selected the pile property as the single property we have defined in the model a moment ago, and we have matched those pile locations with the material properties of the pile. And the loading conditions, what we did was just to apply in the middle of the cap without any eccentricity force in negative directions, which corresponds to the self-weight of the ammonia tank with its load. You have the options to determine and input a variety of loading combinations, such as moments and shear forces, and you also have to ability to define load factor profiling by just using the load combinations, which will just save you considerable amount of time if you want to comply with codes in your design procedure. The connectivity issues are resolved in the connectivity tab. What fixed means is all movement is restrained. No translation, no rotation at the point of pile and cap joints. In a pinned connection, rotation is allowed, but translation is restrained. In a restrained connection, the third option is available. Translation is still restrained. However, a rotational spring value stiffness must be entered, meaning that the rotation is not free. It generates some reaction based on the rotational spring value that you enter. And not to skip, there are also advanced details for defining the pile cap, which is the elevation and length. You are able to define the elevation and length of each pile and modify them, have different patterns of piles connected to the same cap. You can play with the pile orientations in case you have cross sections that do not comply with symmetry, which is not the case for a circular cross section and a homogeneous reinforcement distribution, of course. You have the option to define custom displacement profile for those piles and apply custom reaction curve multipliers. And last but not least, you have the option to define axial and lateral group effect reductions, which will just avoid any mistakes you may make if you just disregard the pile group effects and use only the ultimate capacities calculated. So the total runtime for this model, including 100 and almost 20 piles. It was under 30 seconds. No problems with convergence or so, just smoothly ran, and we have the results. In RSPile pile analysis, you have the option of just directly displaying the displacements, the beam axial forces, shear forces, bending moments, as well as the soil stiffnesses in all directions. So to take a step further, you may stay within RSPile to iterate and optimize your pile design, determine the individual capacities, modify the length, geometry, cross-sectional and reinforcement details, cross-sectional demands, and finally come up with something valuable. Alternatively, you may just take these stiffness values upon evaluation, of course, and put it into more detailed finite element based substructure analysis in RS2 and RS3, or you may share it with your superstructure design team to allow them to model further in their structural software bundles. So I think this concludes today's session. I am not sure if we have just managed the time management section of the session. However, there are still attendees waiting online and who were kind enough to listen to us. And some of them, I know that they are perhaps during their lunch break intervals, and they were patient enough to just listen to us. And for our participants from around the globe in different time zones, thank you for your participation. We have noted all of your questions. In case we're not able to answer them directly within a few moments, please be assured that they will all be addressed. So if you have further technical questions, you may just forward it to us. In our regions of responsibility, if you want to just set up a trial version for any of the Rocscience bundles or sales inquiries, just email to us. Until our next session, which is hopefully to be announced soon, stay healthy, stay safe. We hope to meet with you again. Dr. Miller, I'm handing the stage to you to say the final words as well.
Thank you. Do you think we have the time to answer some questions now? Okay, so I will try to answer the few questions which we have over here. So there is a question from Flavio, which says, who is asking about negative friction and modeling of negative friction on jet grouting piles. So actually, the focus of our study was on piles. We did the parallel study of jet grouting as a comparison. However, if you consider jet grouting columns as structural elements, in my opinion, you can go for a similar approach as for the piles. However, you should be careful with the adhesion coefficient, which should be different than the one which is used for piles, in my opinion. So there is another question which asks about liquefaction consideration in the design and PGA. So PGA was selected according to the location of the site, so 0.15 G. So this is how PGA was selected, based on the seismic hazard map of Bulgaria suggested in Eurocode. So another question: how much settlement is good for a structure? Once again, codes would give you the limits, or some special requirements would give you the limits. In our case, limitation of tilt and settlement was given by the client, but if you do not have such information in some cases, you could probably stick with what is given in the codes. In Eurocode 7, we have a special appendix which tells us what settlement is allowable, what tilt is allowable according to the superstructure type. So we have a couple of other questions left. How to calculate load sharing between piles and Raft in a pile Raft? So I believe that RS3 is a good software, a good approach by adopting the finite element method in RS3 in order to see what the distribution of forces is. So if I were you, I would go for RS3 in this case. So which software is good for continuum modeling of tunnels? I would say that you can do almost anything which has to do with geotechnics in RS3. So I believe that RS2 and RS3 are good options. And I think the last question is how consolidation treatment has been done on this site. So actually, no, I mean, I'm not sure what the participant means by how consolidation treatment was done. So actually, samples were taken from boreholes. They were tested in the lab by performing oedometer tests, and consolidation parameters have been obtained in the lab in order to perform the analysis. And actually, no soil improvement has been done on site, just execution of piles. So by answering these questions, I think we have covered all of them. I would like to thank Anil for your wonderful presentation, which has extended the study. It was very interesting for me to see what your team has done by adopting some parallel approach. So it was really amazing from my point of view. So thank you for that. And by this, I think we have answered all questions. I would like to thank all of the attendees for participating. Presentations took a bit longer than what we expected, but I really hope that your time spent with us is not lost. So you would find some things useful from what you have heard today. Of course, you can always contact me by finding me on LinkedIn. You can find our company, so you can always ask whatever you're interested in based on today's presentation or anything else. So once again, thank you very much.
And for the last words, a big thank you to Rocscience Toronto team. Actually, they have made this possible, and we thank them for their generosity and sharing their excitement through the journey, and just assisting us online right now due to despite 8 hours of time zone difference. So thank you to Rocscience marketing team, developer team, and sales team, whomever wish to take the credit. I'm just closing the session for now. See you.